Ready, Mark? Okay. Well, welcome back, everyone. Are we on? Yeah? Okay, good. Well, thank you for staying this long. I think you are going to find that you're going to be in for a treat. Okay? So I think we have come to an end to the hands-on activities of the Moon Night, which I hope most of you, if not all of you, enjoyed outside. What we are going to do now is to move into the final bit of Moon Night, which this year is going to have a special lecture by a very popular speaker, and I'm sure you will be spellbound during the talk. So let me hand you over to our head of school, Professor Sally Jordan, who is going to introduce this year's Barry Jones awardee lecturer. So thank you for the attendance, and I hand you over to Sally.
Before we do anything else, Mahesh has just drawn the sort of first half of the evening's proceedings to an end. I don't think we can let the opportunity go to actually thank Mahesh for the huge amount of work that he's put into organising it. So Mahesh, thank you very much indeed. So, as Mahesh has said, in a few minutes we're going to welcome Dr. Sarah Ruekheimer to give the 2019 Barry Jones Award Lecture. Before the lecture, I'm going to invite Anne Jones, who's Barry's widow, to present the Barry Jones Award to Sarah. Before, it falls to me to thank the Astrobiology Society for Great Britain, who co-sponsor the award. And I'd also like to warmly welcome all of you. That's all of you who are in the room, all of you who are watching online, and particularly Sarah and Anne for being here, and also to explain how the whole thing fits together. I also get the really exciting jobs, which is to remind you of the safety announcement, the safety regulations for the lecture theatre. We're not expecting a fire drill. If the alarms were to go off, there's a fire escape just past the way you came in, basically, just by Mahesh. There's another one at the back of the room, and the fire assembly point is in the car park at the front of the Beryl building. As Mahesh has said, I'm Sally Jordan. I'm Professor of Physics Education and Head of the Open University School of Physical Sciences. However, back in 1999, so that was before some of you guys were born, probably quite a long time before some of you were born, Professor Barry Jones was head of what was then the Open University's Department of Physics. I was working as an Open University tutor, and a full-time post as a staff tutor, that's a lecturer who's based in the region. I was based in Norfolk, came up in the physics department. Barry was on the interview panel. That was the first time I met Barry. And he was one of those who took a huge risk in appointing me to that post, because I didn't actually, for the adults who understand what I'm saying, didn't actually meet all of the things on the person specification. So he was taking a bit of a chance on this woman here. Barry went on to support me when I'd been appointed, and many of my colleagues also speak of the support that Barry gave them at key points in their career. Barry had joined the OU in 1972. He had a lifelong interest in astronomy and astrobiology, things that Anne will speak about more in a minute. He also had a massive talent for communication with people from all backgrounds of all ages, and therefore it's fitting that the Barry Jones Award is given for outstanding contributions to outreach and the teaching of astrobiology. Dr. Sarah Ruekheimer is Glaston Postdoctoral Research Fellow at Oxford University and a Hugh Price Fellow at Jesus College, Oxford. Her research interests lie in modelling the atmosphere and climate of extrasolar planets, with a particular focus on atmospheric biosignatures in Earth-like planets. Sarah's work's taken her all over the world. She was at Harvard University, working at Harvard University, then at St Andrews University in Scotland, and now at Oxford. Sarah has a particular enthusiasm for teaching, which was instilled from an early age by her father, Mac Ruchheimer, who taught physics at Montana State University. It's noteworthy that a course that Sarah developed while she was at the University of St Andrews, entitled Astrobiology, Life in the Universe, has one of the highest student enrolments at St Andrews University. Sarah was also explaining to me earlier this evening that she sees astrobiology as an excellent way of teaching interdisciplinary science because it links together physics, chemistry, and of course biology and geology as well. Sarah's participated extensively to public outreach, driven by a passion to improve scientific literacy. Her outreach has included visiting local schools, but she also makes appropriate use of technology, including videos, podcasts and blogs to reach a really wide range of audience. Those of you who know what we do at the Open University, and particularly in how we teach, will immediately see how well that is aligned with the way in which we go out to people all over the world. And indeed, even though it was some time ago, with the way in which Barry was inspired in his own teaching. So without further ado, I'm going to hand over to Anne, who will say a few more words, and then to Sarah for the 2019 Barry Jones Award Lecture. Thank you very much.
Thank you very much, Sally, and it's really good to be here and to see so many young people too. So, Dr. Ruchheimer, it is a really great honour to present this award to you, the third Barry Jones Memorial Award. Just let me tell you a little bit about Barry's background. The first introduction that Barry had to his future career was when his father took him to a talk about the night sky at the local TOC H Club. This was a charitable organisation that emerged from a soldiers' club after the First World War. I think he was about 9 or 10 then. And this talk made a big impression on him, and by his early teens, he was buying his own materials to grind his own mirrors, and he made his first telescope. Barry had a varied research career, from gamma rays to infrared rays, from architecture to acoustics, and from seismic signals on the moon to solar energy on the Earth. But it was in the late 90s that Barry became interested in exoplanets, and this was at a time when there were only 5 or 6 had been discovered, and with each new discovery there was great excitement and much celebration. And he called this his golden age of research. But it wasn't just research, because most of Barry's working time, or at least much of his working time and interest, was given to his 2 other loves, writing and teaching. It was through the excellent course material and summer schools that the OU promoted in its heydays, and from his commitment to public education of science as president of the SPA, the Society for Popular Astronomy, through evening classes and astronomy groups, and through work that he did in the local primary schools, he reached many people from many different backgrounds, with many different levels of education, and always with a great enthusiasm for the people who listened to him and for the words that he told them. So it really is very fitting that this award is being given to someone who has very similar interests, a special interest in the existence and the potential of exoplanets, but also someone who has a desire to inspire the common person with her research into the fascinating subject of possibility of life on exoplanets. It really is a great pleasure, Dr. Ruchheimer, to present you with this award.
Thank you very much.
You're welcome.
Well, who can follow that introduction? Thank you so much for having me here to talk to you today. It was very lovely to hear about Barry Jones. He reminds me of my dad, who also did a lot of outreach to students and physics education, and we have a bursary in his name at Montana State University for undergrads, and so it's a real honor for me to be here and to honor his memory. So thank you so much for that lovely introduction. So yes, today we're going to be talking about this question of, are we alone in the universe? So we've been trying to find the answer with SETI, you might have known of this as a search for extraterrestrial intelligence, and we've been using radio telescopes to try to scan the skies for a signal. But so far, we've been met with silence. There's been no hello, Earthlings, call from afar. So, may I ask really quickly, who in the audience believes there's life beyond ours in the universe? Excellent, most of you. So I'm pleased to also say that many people are interested in this, and in fact, Bernie Sanders, one of our presidential candidates, has promised that if he's elected, he will tell us the truth about whether the aliens are real. And maybe you saw this in the news, but back in September, there was this petition that went around, and 2 million people said they were going to raid Area 51 to see them aliens, and they can't stop us all. I think in the end only a couple hundred people showed up, but still it clearly shows a public interest in the topic. So when I said life, what did you envision? Did you envision aliens or aliens? So when I'm going to be talking about when we're finding life on other planets, I'm mostly going to be focused on these guys, single-celled microbes, not necessarily the complex life that we all sort of imagine when we think of sci-fi. And first, in this talk, I'm going to talk to you about how might we actually find life on another planet. And this is really by looking for microbes. Microbes have the largest imprint in our own atmosphere, and they would be the easiest thing for us to see from a distance, far more easy than signs of technology or human activity on our planet. So you might have seen this image. It's the pale blue dot image. So that's Earth, and then blown up here. This was first taken by Voyager 1 in 1990 when it was about 6 billion kilometers away, and we turned the mission back and snapped this picture. And that's us, that's everyone on this planet. And so from that, though, we can break apart that light, that pale blue image, into different sorts of colors of light. And in fact, each molecule and element has its own unique spectral fingerprint. And this is how we're able to see what's in the atmosphere of other planets or things in our own universe. Here is that image again, and if you were to take it and make that spectra and break it apart into all the wavelengths of light, you would see signs of vegetation, of oxygen, ozone, methane, carbon dioxide, and water. And all of these things would tell an alien astronomer that likely there is life on Earth. As mentioned in the introduction, we've actually been finding other planetary systems since about 1995. And the Nobel Prize in Physics this year was awarded for this first discovery of exoplanets around a sun-like star. But we're talking about planets that are very far away. And let's remember that space is big. So we had Moon Day today, and when we think about the Earth and the Moon, we sort of have this sort of image in our brain. But this is definitely not to scale. If we actually put it to scale, that's to scale. That's the Earth, that's the Moon, and all of the solar system planets could fit end to end between us and the Moon. I really recommend taking time after this talk to Google "If the Moon Were Only 1 Pixel," a tediously accurate model of the solar system. It's an amazing website where it has to scale all of the distances and sizes of our planets in our own solar system, and you scroll sometimes for minutes to get to the next planet. Now, it's a fun website because he gives you lots of fun facts on the way of how many movies you could watch in this amount of time and how close you are, but it really gives you a sense of scale of even our own solar system, which is relatively close to us. Another image that I like is the Hubble Deep Field and the Hubble Ultra Deep Field. So this is an image taken by the Hubble Space Telescope where it looked at a dark patch of sky. We didn't know of any known stars or galaxy in that patch of sky, and it just stared at it for a little over 11 days, for 1 million seconds. Now, to put this in context, Hubble is about $1 a second to run. So that image is $1 million. And they were looking at nothing. So you're spending $1 million on perhaps a blank image. But instead what happened is they found this. And every single point of light in this image is an entire galaxy with hundreds of billions of stars. And this image size on the night sky is about the size of a grain of sand held at arm's length. And imagine how many grains of sand could you fit in a sphere all around you, and each one having 10,000 galaxies. So that's this image. It's just simply beautiful. Every single speck, every single smudge, every tiny point of light is an entire galaxy. And that really opened our minds to just how big the universe is and put our place in it to be so much more humble. All right, I promised I would talk to you about finding life on other planets, so let's start. The first step is we have to find exoplanets in solar systems that have conditions conducive to life. And when we think about this, we think about having a surface where you can do chemistry and having liquid water. And liquid water is something that all life on Earth uses. We haven't found a single evidence of life that doesn't use liquid water, which is why we often talk about it. How many of you have heard of the TRAPPIST system in the news? Anyone? This was a couple years ago. It was announced. It was a series of Earth-like planets. So these are all roughly Earth-sized, but around a much cooler star. And so these planets are really close in. And what's amazing about that, because the star is cooler, where liquid water could be on the surface then is also closer in, and in fact encompasses 3 planets in that system. So you have 3 planets in that star system that could have life on it. Now imagine if they all did. And so you could imagine if you stood on the surface, this is an artistic rendition of standing on the surface of one of these planets, the other 2 habitable planets in your sky would be the size of our moon. So you might actually be able to see continents and oceans and forests from just standing on the surface of your planet, because this star system is so much more compact and these planets are so closer together. So I just think that is really amazing, and this is certainly one of the systems that we're going to follow up with our first mission capable of characterizing the atmosphere of exoplanets of this size, and that's the James Webb Space Telescope, which I'll be talking about a little bit later. So we have about 55 or so known currently potential habitable exoplanets. And so we have plenty of places to look, and this number keeps growing. I just looked today, and as of yesterday, this is the number that they're reporting. But I want to keep in mind that habitable doesn't mean inhabited. There are so many factors that go into whether a planet actually can have and sustain life. And each of these areas is a whole range of astrobiology research that's actively being done around the world. So I mentioned that we want to find exoplanets with suitable conditions for life that have surfaces and liquid water. Let's talk a little bit about liquid water. So why do we think there needs to be water? Well, first of, we know that life needs something for food, an energy source, whether that's from the sun or chemical energy gradients, and it also needs a solvent or water to do the chemistry that makes life. Now, a lot of people in talks, they ask me, well, why water? Why does it have to be water? And there's a few things that I'd like to say on this topic. One is that solvents are needed to do chemistry, to break apart molecules and to do other molecules. So you need something that can do this. And water is particularly interesting because it's a polar molecule. This charge difference actually allows it to pull apart other molecules. This is why table salt dissolves when you put it in water. The charged parts of water will pull apart that into the ions, and you can dissolve it in your glass of water. The other reasons, though, is water is particularly very interesting. It's a weird sort of solvent. It has this polarity helps it bond strongly, which makes ice an unusually strong molecular solid. The high surface tension causes the water to actually be able to rise through vascular plants and trees. The surface tension also makes it form water droplets, and because ice floats, you get this water hydrological cycle on our planet. And also, water remains a liquid over a much wider range of temperature and pressures than other molecules. So this is one of the reasons why we're looking at water. And the other argument I just say is water is everywhere. It's everywhere we look, from the moon to Mars and even in the interstellar medium. So water is abundant in the universe, and it seems a good first place to start since we know that all life on Earth uses it. The next thing I want to talk about is how are we going to actually detect these biosignatures? So life can be really weird. You've probably heard of extremophiles. This is life that can exist in some of the most inhospitable environments, certainly to human life. And this is everything from these deep hydrothermal vents that are at really high temperatures and pressures in the ocean to, in my own home state of Montana, these near boiling hot pools in Yellowstone National Park. And even in the ice, the liquid brine layers between ice crystals, life can live. And you see it in Antarctica coming out of this falls here. So life really does find a way. Wherever there's liquid water, it is present. And one of my favorite extremophiles is the tardigrade. Who has heard of tardigrades? Yes, yes, they're amazing. They're also called water bears or moss piglets, and they're amazing. They're up to 1 millimeter in length. They have 8 legs, and each with little claws. They look like these images here. They're a polyextremophile, so they can withstand many different environments. But what's amazing is they're actually complex life. You know, they're not a single-celled organism, and most extremophiles are just those microbes. But these guys are much bigger than that. They can withstand temperatures from well below freezing to above boiling, which is amazing. And they can withstand pressures 6 times the deepest ocean trenches on Earth. How did they evolve that? They're incredible. And they can also withstand ionizing radiation 100 times what we can withstand. And they even put them in the vacuum of outer space with this excellently named program called TARDIS, Tardigrades in Space. And they put them outside the International Space Station for 11 days, exposing them to the vacuum of space, the high energy radiation, the cold temperatures. And what they do is they go into this little stasis state, and when they brought them back in and rehydrated them, they started reproducing and having more babies. So they're incredible. They can go without food or water for 30 or more years. We tried to kill them as long as we've known about them. And those ones, they keep coming back to life, so they seem pretty indestructible. And all of this really boils down to their ability to go into this desiccated state where they can dry out to about 3% or less of their water, only to later, when the conditions are right, revive themselves and forage and reproduce. All right, so what is life? We've been pondering this question for a long time as a scientific discipline within astrobiology. You could try to describe life's characteristics. You could say, well, life grows, and it replicates, it metabolizes, it evolves, it displays complex behavior. But there's a lot of things that are not life that do the same. So crystals grow, computer programs replicate, forest fires metabolize, planetary systems evolve, and lightning and tornadoes display complex behavior. So none of these characteristics in and of themselves make up a definition of life. But you might think back, well, what is water? How do we know what water is? We know from atomic theory that water is H2O. But before that, any definition of water would have been insufficient. You could have tried to describe the characteristics of water. You could have said it's wet and clear, but so are some oils. No single definition would have been complete without knowing that water is H2O. So with only one example of life, are we really in the position yet to have a solid definition of life? Doesn't stop us from trying. So we have the NASA's working definition is the one that's most commonly cited in astrobiology. And it says life is a self-sustained chemical system capable of undergoing Darwinian evolution. So this makes a few assumptions. It rules out synthetic or android or complex AI sort of life. It's saying it's a chemical system, and it's self-sustained, and it's capable of evolving in different conditions. So that's sort of the roadmap that we use when we're thinking about how could we find life on other planets. But what is alive too? I mean, so we have this question of when was there the first life? It's a really hard question, right? So we know things that are rocks are not alive, and we know that a full cell is alive, but what's in between that? We don't have any example, right? Because we're living in a full complex biosphere. We don't see those first signs of the early steps of life. And so you might imagine that there's this aliveness, and note there are no units in this graph here. You might have aliveness and complexity. And George Whiteside's made this comment. He's a professor at Harvard. He said, it's a long way to go from slime to Mozart. But we actually know how to do that pretty well. Evolution describes that pretty well, even the transition from single cell to multicellular life and how things evolved, eyes and everything. We kind of have that pretty well understood. So Steve Benner quipped back, he's a prebiotic chemist, well, it's a long way to go from HCN to slime. And that's really where a lot of the origins of life research is how do you go from just molecules to something that's alive? And you could imagine perhaps there's a series of stepwise functions with each more complex things being a little bit more alive, or it could be that you need to develop that full complex machinery and then it jumps to being alive, or it's a more gradual process. We just really don't know, but a lot of origins of life research in the collaboration I was part of with the Simons Foundation while I was at St. Andrews is looking at this, is looking at these prebiotic steps into how to find the transition from HCN to slime. So we do know that the first living cell did not just spontaneously appear, and it must have risen through a series of emergent complex chemical events. All right, so when we're finding other life in the universe, there are two strategies, right? We can look in the solar system, and we can look on exoplanets. So the solar system is great. There's things like Mars, Europa, Titan, Enceladus, maybe even Venus. These are all places that we can go and visit with probes and landers and actually try to look for different life. And then there's exoplanets, and that's what I'm going to be talking about, but it's really limited to this pale, fuzzy pixel. It's going to be really hard to determine. So what I'm talking about in the rest of the talk is future observations. So this is Earth, Venus, and Mars. These are the terrestrial planets in our own solar system. And those spectra are very different for those three terrestrial planets. Now we expect an even wider diversity of types of atmospheres out there, like with the TRAPPIST system. And so we hope to use, say, the TRAPPIST system and see the spectra and how they vary with different orbital distance from its host star to see if we can start to understand how planetary systems evolve. And my particular research interest is how do biosignatures, what do they look like around different star types? So what I do is atmospheric modeling to determine things like what wavelengths, how big of a telescope do we even need, and what sort of resolution is required in order to make the measurement. We want to do the minimum resolution as possible to get the data because it's expensive, right? And my specific subspecialty within this is how does the star influence the atmosphere, the spectral fingerprints, and the biosignatures. So we go back to this pale blue dot image that I mentioned at the beginning. And in it, I told you you could see signs of oxygen and methane. And the reason why we talk about these gases is because on Earth, all of oxygen is produced by life, and methane is primarily produced also by microbial life, living in anoxic environments like in cows, in digestive tracts of cows. But you can also envision, you can think of ways to get these without life. So you can have high energy light, UV light break apart water or CO2 and get oxygen. Or you could have, we know methane comes out of volcanoes. So if you just had a more volcanically active planet, perhaps you would just see the methane from volcanoes. But on Earth, what happens is we have biology, and it's pumping out large quantities of both of these gases, of both oxygen and methane. But if biology were to shut off tomorrow, these two gases would quickly destroy each other within the atmosphere and no longer be present in our planetary atmosphere. And so this is why, when we think about a biosignature, it's really the combination of things that wouldn't otherwise exist through geology or physics alone. And the strongest biosignature to date is the combination of this oxidizing and reducing gas. So there's some challenges. We have the technological hurdle, even just to make the detection, let alone whether it's life or not. Just detecting oxygen in another planet atmosphere is going to be very difficult. And then, of course, there's the interpretation hurdles. That's understanding what we're seeing, and I would argue that's even more difficult. But let's talk first about the technological hurdle. It's been likened a bit to like finding a firefly in front of a spotlight, but imagine that spotlight is now in the US and we're observing from the UK. And it's even more difficult than that, about a factor of 100, more tricky than that. So it's very hard to try to make this observation. But we've come a long way, and I like to think about the technological improvements that we've had in astronomy over the ages. This is the image of Pluto that we had in 1930, and if you think back to that exoplanet image I showed you, it's kind of similar. Then with Hubble, we had something more like this, and then with some improvements on Hubble, we had this. And now I'm cheating a bit because I'm going to a flyby mission, but we can actually see snow-capped mountains on Pluto. It's amazing. So the technological improvements over the ages have been immense. And when we think about the Juno mission, this took high-resolution pictures of Jupiter displaying complex atmospheric phenomenon that we had never seen before. And these pictures are just simply stunning. You can actually see clouds, and these clouds are made of ammonia and water. And you can see them in the atmosphere of Jupiter. This is my favorite single image from the Jupiter-Juno image. All of these have been color enhanced to bring out some of the effects so your eye can see them more. All right, so going back to these challenges, we have already talked about the technological one. And so we're going to be reaching that state soon. Actually, in the next 10 years or so. We have space telescopes like the James Webb Space Telescope that's launching in 2021. And we have large ground-based telescopes. These are often called ELTs, or extremely large telescopes. Astronomers are very creative in our names. And they each have different trade-offs. And so it's not one is better than the other. They each can do different things. So in space, you get low resolution, but that low resolution allows you to find actually the abundance of a molecule. So how much is in that planetary atmosphere? And that's really important. But from the ground, the high resolution, we can do much bigger spectrometers because we have unlimited space. So you can get much higher resolution, but then you can only just see their presence. You can't actually tell how much there is from the ground. And so this is the trade-offs that you get between these two strategies. But what's amazing about it is you can even detect from the ground minor molecule presence or even isotopes, which is just incredible to think about. And this is using this technique of the Doppler shift. So the Doppler shift is when the planet's moving around its star, its motion is shifting back and forth the spectral resolution lines that we're observing. Just kind of like a siren when it passes you in an ambulance, the pitch changes that you hear. The same thing happens for all light when it's moving. And so this we'll observe this spectrum and the motion there. And like I said, we can even tell the difference at sufficient resolution to isotopes. And that's just the difference of one neutron. So you have hydrogen and deuterium, for example. And what's amazing about this is if we look at the high resolution spectra of, this is carbon monoxide with C12 and this is carbon monoxide with C13. So just the presence of an additional neutron, and these are the two spectral high resolution lines. They're different, they're clearly different, and we could tell that difference from the ground. And so that's pretty incredible to me. And in fact, we could detect this in a hot Jupiter this year with technology that's already available. And we could detect HDO, or heavy water, in our nearest habitable planet, Proxima Centauri b, with the ELT and a coronagraph in just one night of observations. So this is incredible to me. I never thought this was possible when I first heard about this at a conference last year. But basically what they do is they use high-resolution template of the molecule, and they march along your observation. And when you get a match, then you have this spike, and then you know you've detected the molecule. So this is how they're able to tease out at high resolution the presence of these minor features. I want to take a little moment and just talk about squiggly lines, because I never thought I would be an astronomer. I was not interested in astronomy as a kid, or even physics. So as I mentioned, my dad was a physics professor, and I remember coming to him as I was about to graduate high school and I was choosing my senior year courses, and I said, Dad, I hope you're okay with the fact I'm never going to take a physics class as long as I live. And my dad said, that's okay, you got to major in what you want to major in. He was a very supportive dad. And so I signed up for accounting, which was very boring. Sorry if there's any accountants in the room. And so the only class that would let me take me that late into the semester, because I changed my mind, did not want to do accounting, was physics. They were like, we'll take you, come on in. And I really liked physics. So I realized at some point, in my first year of college that it was stupid not to major in it just because my dad did it, and my brother did it, and my sister did it, and my other brother did it. They all do physics. So eventually I got over that point and I did a physics degree myself. But I hated astronomy. I never took a single astronomy class. I thought it was useless, all this order of magnitude nonsense that you don't know anything to within like factors of hundreds. And I had this friend who was doing this astronomy summer research project, and all day long he was just looking at spectra, these squiggly lines, and saying yes, no, yes, no. And I was like, this no, never, never. And so I remember I was in my 4th year of undergrad, and a professor asked me if I would do a project with him, an astronomy professor on spectra. And I demurred and said no politely about 5 times, but he kept approaching me, and I think on the 6th time I just said, I don't want to look at squiggly lines all day. And he said, but it's what the lines mean. And yes, I now agree. I now agree with that, but at the time I didn't. So it was after I graduated that I went to a conference and sat in on a session on astrobiology and just got so excited that for the first time in human history, we're close to being able to find objective signs of life on an exoplanet. And how do we do that? We look at squiggly lines. And that's what got me into astronomy. All right. So we'll go back to the interpretation hurdle, because like I said, it's going to be difficult. It's going to be a fuzzy, pale blue pixel. Now, there's one type of detection that would definitely be unambiguous, and that's this sort of hello Earthlings call. We would know that that's life. But barring that, we're going to be faced with the interpretation hurdle. And conveniently, this is where my research fits in. So I think often when I talk to the public thinks that we're going to find this, that we're looking for Pandora in Avatar. We're going to find tall blue people with tails. It's going to be very exciting. And in reality, what theorists like myself claim we're going to find is this very beautiful spectra with very clear signs of life, and it's going to be very easy to interpret. And the reality is we're going to find this, pale blue pixel. There's going to be many models. There's going to be large error bars, and it's going to be hard to interpret. We're going to be arguing about it for decades. So when we think about the interpretation hurdles, we could look for unique biosignatures with maybe that high resolution technique I told you about. So these are signs that these are molecules that are only produced by life. They have no geological or photochemical false positive. The pros of this is yeah, we can't think of a way to make those without life. But the con is they're usually rare and limited to a single microbial species, an evolutionary quirk, so to speak. They're only produced in small quantities, and we don't even have the spectra for them. In fact, we only have, of the 16,000 possible molecules that life could produce, we only have spectra of about 0.04% of them. So there's a lot of basic science that needs to be done before we're able to overcome that. Now, we could look for alternative biosignatures. This is, again, always a question that I get at public talks. The pro here is clear. We're not being Earth-centric if we're trying to expand our concept of what life could be. And in fact, one of my friends who works at MIT, Clara Sousa Silva, she has postulated that phosphine could be a biosignature and has observable features. I think for these, definitely we should be searching solar system planets and the moons around various solar system planets to look for that sort of weird life. And if it exists, that would be amazing. So the cons, though, of course, is we just have no idea what these biosignatures would be for something that's an alternative biochemistry, or if they even exist. And we can't tell if there's life in our own backyard yet on these planets and moons that are close to us. So we're just not in a position yet to be able to answer this question. So this gets back to searching for Earth-like life. Now, the pros here is we might actually understand what we see. Oxygenic photosynthesis uses radiation from the host star, light, carbon dioxide, and water. These are all abundant in the universe. And I would say this is the biggest reason why I think this is a useful strategy, because they are abundant in the universe, and carbon is more abundant than silicon, and carbon forms more complex bonds than silicon and has more complex chemistry. And as I mentioned with water, water is polar and has these unusual features. So those are all reasons to look for these sorts of biosignatures, and there's no shortage of places to look, with about 40 billion Earth-like planets in our own galaxy. The cons, of course, is all of these classic biosignatures, oxygen, methane, ozone, they have known false positives. And so you can't use a single gas. If you take one thing away from my talk, that's what I want you to take away from tonight. And we could still be fooled. We can't visit the planet, right? We can't go to the surface and see it. They're too far away. And so we're going to need multiple gas detection, and that's more expensive. Really, we need to understand the host star. Conveniently, this is what I do. And so I'm going to talk a little bit about that. So broadly speaking, you have hotter stars and you have cooler stars. And the hotter stars have more UV and the cooler stars have less UV. And UV destroys some biosignatures, such as methane, for example. And that could make it harder to detect in a planetary atmosphere. But UV also produces some biosignatures, like ozone, making it easier to detect. So the play of UV is important to understand when we're thinking about these observations. This is an example of all the stars in our nearest neighborhood. 10 parsecs is about 33 light years. And the stars like our sun are G stars, so there's about 20 of them out of the 300 stars near us. Most, by far, are these small M dwarfs. These are stars that are much cooler, much dimmer than our own sun. and they make up 75% of the stars in the universe. And Kepler has found actually that 1 in 4 of these M dwarfs have a habitable planet, so they seem to be good places to first look for life. The problem is they have strong flares, strong UV environments. We don't even know if they're capable of having atmospheres at all. And so, and they also have all of the false positives. Most of the false positives are most strong for these M stars. So you can imagine, say you have this M star which has these strong flares, and it breaks apart water into hydrogen and oxygen. And then the hydrogen is light, so it escapes to space, and then your planet is left behind with a bunch of oxygen in its atmosphere, and depending on how much reacts with the surface, you could see oxygen, but that wouldn't be from life. And it has lost all its water and is no longer habitable to boot. So I hope I've convinced you that the UV really matters. And more importantly, that no single gas is enough to claim life. And I'm sure we're going to see this in the newspaper over the coming decades, so please keep this in mind. And so that's really my main takeaway from this talk that I want you to remember. And this is why this combination of gases, like an oxidizing and a reducing gas together, are the most strong biosignature. I want to also talk briefly about the fact that geological time is long. So not only is space big, but Earth has been around for billions of years. And planets are unlikely to be just like modern Earth. Earth itself has gone from this hellish Hadean world to a snowball state to the Jurassic period. It's in fact, I like to think of Earth as having been many planets and many different types of planets through its history. So one exercise I like to do is think about the history of life on Earth and just scale it to 1 hour, about the length of this session. So you have the formation of our solar system about 4.6 billion years ago, or 0 minutes into the hour. We don't know when the origin of life happened, but it happened somewhere pretty early, we think, because we have signs very quickly, but maybe 9 minutes into the hour or so. Certainly we have the oldest signs of life dating back to 3.5 to 3.8 billion years ago. That's 14 minutes into the hour. Oxygenic photosynthesis at least is as old as 2.7, if not older. That's 25 minutes into the hour. But you didn't get multicellular life. This is why I'm so interested in microbes. You didn't get multicellular life until about 1 billion years ago, or 47 minutes into the hour. And land plants were about 500 million years ago, or 53 minutes into the hour. And then anatomically modern humans, that's people that you'd recognize as your brothers and sisters, have been around 250,000 years, or about the last second of this hour. So in that time, the atmosphere's changed. We've had different amounts of oxygen and methane and carbon dioxide. And so I just want to show you for kind of the nugget of the talk is we're going to venture into real science territory here, because I'm going to show you a slide from one of my own papers. And so there's going to be a lot of squiggly lines on it, but I'm going to walk you through it very slowly. So you pick, say, 4 geological epochs in Earth's history, and then you look at what would those biosignatures look like through time around all the different stars that I was telling you about. Okay, so in the first panel here, we have an abiotic atmosphere. So this is before you have life. And these stars, the colors are these cooler stars, or the red colors, and you go to hotter stars with the blue and the purple. This is when you have the first rise of oxygen, so only 1% of current concentrations of oxygen. You already start to see a huge ozone feature, which is interesting, but only for some star types, not for all star types. And then for the second rise of oxygen, as oxygen largely rose in 2 steps, you start getting that ozone feature for a lot more stars. And then, of course, for modern Earth, you have a strong ozone feature for all stars, and you have methane and water and carbon dioxide and everything. So again, the goal is to kind of try to see both of those features, a methane and an oxygen at the same time. And that's what we're going to be looking for. I want to kind of think, as we come to the close of this talk, I love this quote by Richard Feynman. Science is a way of trying not to fool yourself. The first principle is that you must not fool yourself, and you are the easiest person to fool. We want to believe that we've found life or that we've detected life. It's easy for us to believe things that align with our own worldview. So we have to be really careful. We're going to be facing and overcoming these technological hurdles soon, with the James Webb Telescope launching in 2020 and these large ground-based observatories coming on in the 2020s. I'm really excited. These are going to be able to do a handful of planets. I'm not an observer, but I've been told, like 1, 5, not very many planets that are Earth-like. They'll be able to do bigger planets, Jupiter-sized planets, Neptune-sized planets, but not the Earth. Just a few. We'll definitely do the TRAPPIST system, for example. But really, for the 25-year horizon, we need a bigger telescope. And that telescope could do hundreds to thousands of Earth-like planets and be able to detect the biosignatures in them. So I'm part of a mission concept team in ESA to try to fly one of these things, and that will be really exciting. Because ultimately, we're going to be left with, especially with only a handful of planets, we're going to have this interpretation hurdle problem of what are we seeing. But I'm pretty optimistic. You know, as we know, we're just orbiting a small star in the middle of a spiral arm galaxy, and there's hundreds of billions of galaxies in our universe, and we're really going to be trying to find these molecular fingerprints of life. But I'm wondering, even if we're not alone, will we be satisfied? If we detect microbial life, is that enough? If we detect even complex life, like a ladybug, is that enough? I mean, that's pretty complex. That's, you know, already, like I said, very billions of years have passed. Or really, do we need that intelligent Earth signal for us to be satisfied? So even if we're not alone, will we still be lonely? And with that, I'll take questions.
Thank you very much. Very, very interesting indeed. Opens up a lot of scientific questions and philosophical questions. I'm sure you have the answer to all of them. So do we have any in the audience? If you just wait for the microphone to reach you before you give your question. Thank you.
Well, when we were talking about the different types of telescopes, like ELTs, what did JWST stand for?
Oh, yeah. It's the James Webb Space Telescope, and it's often just shortened. Astronomers have these horrible acronyms for everything, and when I was a student, when I first started at Harvard, I felt really out of place because I'd never taken an astronomy class, right? And all of a sudden I was in astronomy courses, and I remember people saying HST, HST, and I was like, what's HST? Oh, it's like Hubble Space Telescope. Right, okay, I know that. But it took me a long time to learn the acronym, so I should have said it, definitely.
Do you think that you might be the one to discover that there are aliens in the universe?
Wouldn't that be amazing? So I'll probably be working with a team of people. So I'm a theorist to interpret the observations, but I won't be the one making the observations, likely. So, it's always these papers and these proposals are a team of both observers and theorists. I do the theory part of how, can we say this is life? And then some observers making the detection. So it'll be a team of people, I'm sure. But I would love to be a part of it, of course. Yeah.
We do have time for at least one, maybe two more questions. Young lady at the front here.
Are we anywhere near finding aliens, or are we like really far away from finding aliens?
I mean, that's an interesting question. So I'm about to make a bet with a professor at Oxford of when are we going to find the first robust biosignature of life. So I've been thinking about it. I think we have the first chance within 10 years. And that's, we'd have to be really lucky to have a really excellent spectra that looks very clearly like life. But as I mentioned, those first telescopes are only going to be able to do a handful. I think we're probably going to have to wait for that 25-year horizon when we have a bigger telescope and we can compare the atmospheres of hundreds to thousands of planets to have a better idea. So my money is more on the 25-year horizon. Though people at NASA and have been asked this question, people tend to say answers between 10 and 25 years. So I think we're close. I mean, I think, yes, in our lifetimes. Yeah.
I've got a follow-up to that myself. So you talked about the danger of just using a single gas as the signature. What's the risk of false positive if you were to suddenly get this really good signature of oxygen and of methane? How confident would we be that that was life?
I'd be pretty confident.
Brilliant.
It's very hard to sustain both of those gases on geological timescales. You could maybe imagine, an isolated incident that might create them very quickly, but they react very fast, and they go out of the atmosphere, certainly at detectable levels. So I'm very interested in this question. Can you conceive or contrive of a planet that does have both and is produced just by a more active, say, volcanism and some runaway photochemical process. But if you're also seeing water, that eliminates some of those false positives, and knowing the UV of the host star eliminates some of those false positives. So I'd want a little bit more information, but I'd be pretty convinced with oxygen and methane.
It's quite amazing, isn't it, really, because that puts it on it does put it on your lifetime.
Yeah, I hope
Possibly
so.
not mine, but yeah.
If you actually find these signatures, that's going to be a pretty profound thing. That's the first time we have discovered life elsewhere in the universe. But as scientists, we sort of get tied up in the project that we're working on, but we always have to be thinking about what next. So if you do find that signature, what next?
Right. Well, I think it's not going to be quite so easy. I think we're going to argue about it for a long time. Just as the Allen Hills meteorite claim, you might have heard about this in 1992 with the Martian meteorite, and is there life in that meteorite? There are still papers being published in the last few years going back and forward on whether those smudges are life or not. Now, the rest of the world has kind of moved on, and we don't think that that's life, but it still is an active area for those two teams battling it out on whether there's life. I think with an exoplanet, it's even going to be more so. I think one of my fears, though, is that when we actually do detect microbial life, people will be rather underwhelmed, because I think they think we've already found it. In the sense that when we say we found a habitable planet, I think people sometimes often think that means there is life on it, or that we're hiding the presence of aliens from them. I've been asked all of these questions many times. So I think that, honestly, a lot of people think that we actually already have found it. So I think I'll be really excited for and I think it should be a very exciting event for the whole world, and I hope that importance of that event is really properly felt by humanity, because it will be putting our place in the universe ever so humbly.
Thank you very much for the questions, everybody. First thing I'd like to do in the closing statement is just to once again thank Dr. Rukheimer for giving her such a wonderful talk.
Thank you.
And then obviously thank you everybody very much for attending. And thank you very much to Anne for giving the introduction, and to Sally for giving the pre-introduction and for obviously running the microphone as well, yes. Oh, and Mahesh for letting us couple our Barry Jones Award lecture to the Moonlight that he's hosted here today at the Open University. And with that, I guess it would be nice to see you all again next year, and thank you very much.
Thank you.
Thanks very much. Very good. Thank you.